there are often guidelines behind the type of counting that we want to do, and here is one of them. Suppose you want to count the number of ways that R items can be chosen from n of them. Okay, where R is less than or equal to n. So in other words, I have n total objects, and I want to select R of them. Well, the most that I could select is all of them. I can't select more than there are items. I can't select more than n, but I could select as few as 0 and as many as n. So this is our little stipulation on that. And also, let's say the following two principles apply. First of all, items that have already been selected cannot be selected again. So I like to think about the idea of if I'm going fishing in a pond, and I have a few different fish here, I'll use my artistry, and if I catch one of those fish and I take it home, that fish is no longer available to be caught again. And also, if the order in which those items are selected is important, okay, so if the order in which I select the fish becomes important, then each outcome is called a permutation. The number of outcomes is called the number of permutations. So here's an example. Consider the word cat, C-A-T. How many words can be formed from these three letters? Well, assume that those words don't have to be meaningful, but how many ways, in other words, can I rearrange these letters in? Okay, well, of course I have C-A-T. I can do C-T-A, just rearranging those last two letters. I could have C in the middle position, and then I could have T-A in the first and the last. I could have C in the middle position, A in the first, T in the last. Oh, there's a word, act. And then I could also have C in that last position. I could have T-A-C, or I could have C in the last position, have A-T-C. So we could list them all out. There are 6 possibilities. Another way we could think about this is the first letter, L1, L2, and L3. And I could draw a tree diagram and say, well, the first letter could be one of 3 possibilities. It could be C, it could be A, or it could be T. Okay, now notice that this does satisfy our criteria. We can't select the same letter twice. We're just asking for the number of ways that we can rearrange these 3 letters. And also the order is important, right? Because each of these 6 sequences forms a different word, so to speak. So in branch 2, the difference here is that if C was selected as the first letter, then there's only 2 letters left for that second letter. There's A or T. If A was the first letter, then only C or T are left to be selected. And if T was selected first, then I can make letter 2 a C or an A. Now, if I had C and A as the first letter, then that only leaves 1 letter remaining. There's specifically T available. If C was the first letter, T was the second letter, then only A is available for the third. A, C, T, A, T, C, T, C, A, or T-A-C. Right? So every branch omits one of the possibilities from the previous branch. And if you look at this for a moment, you're like, okay, well, I see that there are 6 different possibilities. How could I do this without listing them all out? Well, we can think about this another way, and we can say, let these 3 lines represent the number of possibilities at each letter. So here's letter 1, here's letter 2, here's letter 3. There are 3 possibilities for the first letter. And each of those 3 possibilities, notice, has 2 branches coming off of it to form a pairing with the second letter. So there are only 2 possibilities. Each of those 3 letters can be paired with only 2 other letters. So you notice there are already 1, 2, 3, 4, 5, 6 possibilities at that third letter. And now, for letter 3, because 2 of them are already gone, they're 2 fish have been pulled out of the pond, we only have 1 possible letter for the third letter. And so this gives us 6 words, and I won't put the quotes on that, but 6 different words that we can form. So we have sort of, hey, let's list them all out approach. We have, let's come up with something a little bit more formal so that we don't miss any arrangements. And then let's do it without listing any arrangements at all. And of course, this approach is probably the best. I think sometimes it's helpful to begin a tree diagram to help us visualize things a little bit and to find a pattern and then move on to this. But sometimes it's just necessary to start with the counting approach. So there are 6 words. We call these 6 permutations because, once again, we had n items. So we have n equals 3 items. We're selecting r equals 3 of them. So notice that we're choosing all 3 of those letters. And again, that stipulation of r is less than or equal to n applies here because we can select at most as many as we have. Let's look at another possibility. What if we took the word cats? So now there's 4 letters in that word, but the question is how many 3-letter words can be formed from this word? Again, assume that they don't have to be meaningful. Well, again, we could start listing them out. We'd have definitely these 6 possibilities because we don't have to use S, we just have to use 3 letters. But then now we have to look at all the possible words that we can form with one of them being an S. And we're not going to go ahead and begin listing them out, but you can kind of imagine the only difference here is for letter 1, there are now 4 possibilities. C, A, T, or S. But if C was selected as the first letter, now there are only 3 possibilities, namely A, T, and S. And by the way, the number of branches extending out of A, T, and S will also be 3, except that the 3 branches on the letter 2 column will be C, T, and S as possibilities since A has already been selected. And remember how I said in example 1, sometimes we just start off by listing a tree diagram to get a visualization, and then we let something like this do the computation for us. So if C and A were selected for the first 2 letters, then only T and S are available for that 3rd letter. So notice that we have 4 possibilities here. Then for each of those first letter selections, there are only 3 possibilities in the second table. That'll be the same thing for this guy, for this guy, and for this guy. And then depending on what the second letter was that was selected, there are now only 2 possibilities. So I've just kind of started listing this tree diagram to get the visual that gives me everything that I need in order to know how to use a multiplication principle to come up with the number of possibilities. So there's 4 for the first letter. Each can be paired with 3 possibilities for the second letter, each of which can be paired with 2 possibilities for the 3rd letter. 4 times 3 times 2 is 24. So there are 24 permutations where n is 4. We have 4 letters. We're only going to pick 3 of them. So here's a more interesting problem. Of course, we're not often interested in looking for rearrangements of letters, but again, it illustrates the idea of counting. So let's just put this instead of letters. Let's say that we have 8 candidates, and instead of selecting 3 letters from 8 letters, let's say we're going to try to fill 3 different board member roles: president, vice president, and treasurer. So we have a pool of 8 people. From them, we want to select 3 of those people. And our criteria is again satisfied because we can't have one board member or 2 different positions be filled by one board member. So it just doesn't work that way. We can't have Jane be president and vice president, and we certainly can't have one person take on 3 different roles. So yes, certainly items that have already been selected, so people that have been chosen, cannot be selected for another position. And the order in which they're selected is important. Well, why is that in this case? Well, it's because they're three different roles. So having the sequence of Jane, Dave, and Sue, Jane being president, Dave being vice president, and Sue being treasurer, is different than Sue being president, Jane being vice president, and Dave being treasurer. So the arrangement, the order in which these three people are selected does matter. So let me again start off with a tree diagram here. I have three different board member roles: president, vice president, and treasurer. So I'll start the root of my tree. So who do I have available for president? Well, any one of the 8 candidates, right? Candidate 1, candidate 2, all the way down to candidate 8. So notice how I'm just beginning to map this out so I can see what's going on here. I see that there are 8 possible ways I can fill the president role. But then for the vice president role, if candidate 1 is selected for president, now only candidates 2 through 8 are available to fill the vice president role. So you see we've lost one candidate because that person is in the president role. There are only 7 ways we can fill the VP role. That's the same thing for if candidate 2 were the president. Now vice president could only be 1, candidate 3, candidate 4, all the way up to candidate 8. So there's still 7 different people that can be selected. And then for treasurer, you can imagine now that if candidate 1 is president, candidate 2 is vice president, then the treasurer can only be one of candidates 3 through 8. And again, this top rung of the tree just helps me get enough of a sense to see that I'm counting permutations here. In my case, there are 8 people that could fill the president role, 7 people left to fill the vice president role, 6 people left to fill the treasurer role. 8 times 7 is 56. 56 times 6 is 336 permutations. Okay, in this case, the permutations represents the number of boards that can be formed. So there's a lot of different ways that those 3 seats can be filled. There are 336 of them. And remember, that includes the same 3 people multiple times, except in just different rearrangements of those positions. So president could be, like we said, Sue, vice president, Dave, treasurer, Jane, or Jane, Dave, Sue, or Jane, Sue, Dave. And there are a number of ways that we can rearrange those 3 people. But they're all important because we're assuming that the first person listed is the president, then the vice president, then the treasurer.